Okay, we're going to do a video now on the use of formulas and the formula sheet for studying for the final exam. So when you take your final exam and when you do anything else with the material that we've covered and you're asked to do anything that regards statistical inference, we've learned that statistical inference refers to testing and confidence intervals. And we also said estimation, but we're not going to focus so much on estimation. So really it's testing and confidence intervals. So anytime you look at a problem, you have to ask yourself a few questions about what's going on and what they're asking for. They might ask for a test or a confidence interval, so you need to classify the problem based on what it's asking for. Let's do this. Then you also need to decide if you're talking about a proportion or if you're talking about a mean, or maybe multiple proportions or multiple means. So you can think of this kind of as a table wherein every problem you read will put you into one of these cells. You might be talking about a test on proportions, a test on means, a test on confidence interval, or a confidence interval on proportions, or a confidence interval on means. Then you need to decide, are you talking about one proportion or two proportions, or one mean or two means? So if you're talking about a test on one proportion, you're testing whether your population proportion is equal to some value p naught. That would be your null hypothesis. Your alternative will be that p is not equal to p naught or greater than p naught or less than p naught or something. But I'll just write the null here. In a test of two population proportions, you'll test whether p1 is equal to p2. Which we learned you can rephrase as p1 minus p2 equals 0, depending on whichever way you want to think about it. And then once again, the alternative will be a less than sign or a greater than sign or a not equal to sign, where the equal sign is. In the test of a mean, you'll be testing whether your population mean is equal to some parameter mu naught, some number. And the alternative, once again, can be defined as well. In the test of two means, you'll be testing whether mu1 minus mu2, well, whether mu1 is equal to mu2, or if you want to think of it the other way, mu1 minus mu2 is equal to 0. So ask yourself three questions on every problem. Is it test or confidence interval? Is it a proportion or mean? Is it one sample or two? It's worth noting that with means, things were a little more complicated than what we're saying here, because you might alternatively, instead of having a mu, you might have a mu t, the mean of a whole bunch of differences, equal to 0. So that can also happen, of course. In the two sample means down here, you're going to have to decide if you're pooling or not pooling the data in order to estimate sigma, or sigma squared. So that is another complication, but that's an additional question you can ask yourself. Now for confidence intervals, you're just trying to estimate a population parameter with a confidence interval. In the case of one proportion, you're trying to estimate that proportion. With two proportions, you're trying to estimate p1 minus p2. With a mean, you're trying to estimate mu. With two means, you're trying to estimate mu1 minus mu2. Of course, you might be trying to estimate mu d if your population consists of a bunch of differences. And down in the two sample means, you might be pooling and you might not. So you can ask yourself that once again. But if you think in terms of this table, and when you read a question, you tell yourself, you figure out where you are on the table, maybe you decide, oh, I'm right here on the table, then you know what to do. You need a confidence interval for a difference of two proportions. So let's look at the formula sheet now in terms of the formulas for all of these different scenarios. We have one general formula here, but everything else are formulas that pertain to that table that I just made. So it looks like the top half of the formulas give us formulas for confidence intervals, and the bottom half give us formulas for tests. And then within confidence intervals, it looks like the first two give you confidence intervals for proportions, and within tests, the first two give you confidence intervals for, give you tests for proportions. And then you have the next 5 formulas which pertain to means, and the next 4 down here which pertain to tests of means. Furthermore, once you look inside of means, well, okay, so within proportions here, confidence intervals for proportions, you have 2 formulas. There's the 1 sample formula, there's the 2 sample formula. That happens down with tests as well. 1 sample or 1 population, 2 populations there. Then for the confidence intervals, we have 1 population. We have 1 population, but we have differences, a population of differences. And then 2 populations, 2 populations, and 2 populations. This one is for not pooling. It's the general test, which always works. Sorry, the general interval, which always works. And then this one is for pooling, and it just so happens that when you pool, you need an extra formula because you need to calculate s squared sub p. So that's what the other formula is down here. Gives you s squared sub p. Likewise, in the testing section, we have 1 population mean, 1 population of differences means, the mean of 1 population of differences. You have 2 populations when you're not pooling, and then you have 2 populations when you are pooling down below. And once again, you need a formula for s squared sub p. So you'll look back up here and use that formula right there. Noting, of course, that this is not s squared, it's just s. So you'll have to take the square root when you use it right there. So let's look at a couple of these formulas and make sure we know how to use them. If you were asked to find a confidence interval for a population proportion, you need a p hat. That's the population proportion. And sometimes the problem gives you p hat, sometimes you have to calculate it. We know p hat is just the number of successes for whatever you've defined as a success in your problem, divided by the number of trials, or the number in your sample. So you can calculate your p hat. We know what n is, and that gives you everything except for z star. Z star is your multiplier. It comes from R, and it will be from a command that says q norm, and then 1 minus, well, no, I'm not doing that right. Alpha over 2 is what it is. Q norm of alpha over 2. Where alpha, the confidence level, like 95%, equals 1 minus alpha. So that gives you your z star, also your z star in the 2 population proportions confidence interval. You have a p-hat 1 and a p-hat 2, which you can calculate the same way as this for each sample if you need to, as the number of successes in that sample divided by the number of trials. Number of trials, or sample size, in the denominator, and p-hat 1 minus p-hat 2 right there. Now moving on to confidence intervals for means, you have x bar, that is the average of your sample, or d bar, which is the average of your sample of differences. You have S, which is the standard deviation of your sample, or S of D, which is the standard deviation of your sample of differences. And your sample size, T star sub n minus 1 is, once again, because it's a star, it comes from Q, but it comes from QT. And so you would ask for QT alpha over 2, comma, then you need to put in your degrees of freedom, which is n minus 1. And that gives you the T star. For two samples, x bar 1 minus x bar 2 is just the difference of your sample averages. You also have sample standard deviations for the two samples and sample sizes for the two samples. Your T star here is calculated the same way as above, but your degrees of freedom will be the smaller, that's what min means, the smaller of n1 minus 1 and n2 minus 1. If you need to pool, the only thing that changes is that you'll calculate s squared sub p using the formula down here, which is a function of quantities that we're already familiar with, the n1s and the s1s. Then you put it in, calculate everything. Your T star is calculated the same way as above using QT, but your degrees of freedom are now n1 plus n2 minus 2, which will go in place of the n minus 1 here. On to testing. Testing, we know, has 5 steps. You define your hypotheses. You want a test statistic, which is what the formulas are right here. You want a p-value. You want a decision regarding the null hypothesis. And you want to interpret your decision in the context of the problem. So, your test statistics are here. You'll either get a z-test statistic or a t-test statistic. In the case of a 1 population proportion, your test statistic is p-hat minus whatever your null hypothesis says that p is equal to, some number, over the standard error, which uses p0 once again. In the case of 2 population proportions, you need a difference, and then you'll have the standard error given down here. In the case of 1 population mean, you'll have your sample mean minus the value of your mean under the null hypothesis, over the sample standard deviation over the square root of n. That works similarly for the 1 population of differences mean, where you start with your sample mean, divided by the standard deviation of differences over the square root of n. And then for 2 population means, you'll have the difference of their sample averages over the standard error. And if you pool, it's the same way, except you need SP, once again calculated up here. So, you'll need to always define your hypotheses, your null hypothesis, and your alternative hypothesis if they're not given to you. A hypothesis is always stated in terms of a parameter. If you do not have a parameter, a p, a mu, a p1 minus p2, or a mu d, or a mu1 minus mu2. If you don't have one of these things in your hypothesis, you have not done the hypothesis right. It should not reference an x-bar or a p-hat, it should reference parameters. So, your null hypothesis will be that some parameter is equal to some value. In some cases 0, in other cases not 0. And then your alternative will be that that same parameter is less than or greater than or not equal to the value. You won't write all three of these, you'll choose one based on the context of the problem and write it. Your test statistic is given as above, as we talked about. Your p-value, you will always sketch a picture first of all. It will start with the normal distribution. This is a sampling distribution of a statistic. It might be x bar, it might be p hat, or whatever statistic corresponds to the parameter in your hypotheses. You'll write where the mean of that sampling distribution is under the null hypothesis, which will be whatever number is right here, according to your null hypothesis. And then you'll plot where is the actual number we calculated in our sample. Where is our value of x bar, or our value of p hat, or something. Maybe it's right here, for example. And then you shade under the curve according to what the alternative hypothesis says. If it says less than, then you know you need to shade it for all values less than what you found. If it's not equal to, it won't just be the one tail, it'll be the symmetric other tail on the other side. If it said greater than, it would be everything greater than the value you saw, which could be a large part of the curve, but usually you don't shade a large part under the curve, although it can happen. And then your p-value is calculated using the letter p, either followed by norm or followed by t, depending on if you're talking about a mean or a proportion. P norm of your test statistic z, or if you're doing a mean, it would be p norm of your test statistic t. And in the case of the test statistic for means, you would need degrees of freedom here, which we can see are either going to be n minus 1 or the minimum of n minus 1, n1 minus 1, and n2 minus 1, or n1 plus n2 minus 2, depending on which one of these you're doing. And then sometimes you'll need a 1 minus, depending on which area you're going for, and sometimes you'll want a 2 times. Not always, just this part is in special cases you'll need either the 2 times or the 1 minus or both in your p-value, depending on which tail you drew. Your decision is always to reject or fail to reject the null hypothesis, and if that's all you say, that's fine. You don't have to say more than that, although you can. Reject or fail to reject the null. And then your interpretation will always start out with the words, there is statistically significant evidence if you rejected, or there is not statistically significant evidence if you failed to reject. There is or is not statistically significant evidence that, and then you put into words what the alternative hypothesis says. There is not statistically significant evidence that p is greater than 0.6 or something. Except it's better than saying p is to say what p actually stands for. There is not statistically significant evidence that the proportion of dogs who can swim is greater than 0.6 or something. And that will give you your test, and you'll be done with those 5 steps. Well, I marked up this formula sheet pretty good. If you have any questions, feel free to email me, but I hope that helps you know how to use this page here, and I look forward to seeing you tomorrow in the final.